Well, thank you for having me. So one of the things that I think was just mentioned is that we try to build these really resilient systems, and it would be great if everything we used was serverless, but unfortunately that is not the reality. We have to deal with a lot of different applications. So I'm Daly. I'm the CTO at a small company in New York called AlertMe. I work actually out of Massachusetts, out of Boston. I do quite a bit of consulting with companies in the cloud. I have been working with startups for a very long time, and I just recently stopped dyeing my beard to get rid of the gray. I started working with AWS very, very early, like right after sort of EC2 was launched, so I've been doing that for quite some time, and then as soon as Lambda was launched, I sort of fell in love with that and started doing quite a bit with that. I do have a blog, jeremydaly.com. That's quite an echo. And I also do some open source work and do some speaking. I have my Off by None newsletter, so if you want to follow all the latest serverless news, check that out. And then I also have my Serverless Chats podcast, so there's some stickers and stuff around if you haven't gotten one yet. And I'm also an AWS Serverless Hero, which is a great program which allows me to kind of talk about some of the benefits that AWS has, and they help support the work that I do. All right, so today we're going to talk about a couple things. First, we'll talk about what is resiliency and what is serverless, because obviously you're at a serverless conference, so I'll tell you what serverless is, but more so I'm going to tell it in the context of this talk. We're going to talk with working with less than scalable databases, relational databases. We'll talk about unreliable APIs, how to manage API quotas, and a little bit about decoupling our services, and then we'll talk about a few other non-serverless components. So first, let's start with what is resiliency. A lot of people get resiliency and reliability confused. Resiliency is not about preventing failure. It's about being able to recover from it and to make sure that your system can continue to provide some sort of acceptable level of service, even if part of the system is down. So it's not about preventing failure. It's about being able to sort of gracefully deal with it. So what I like to say is reliability is about staying on the horse. Resiliency is about getting back on it after you fall off. All right, so what does it mean to be serverless? So AWS and a couple of other companies put these sort of things out where they say there's no server management, and it's flexible scaling, and you pay for value or scale to zero or whatever, and then automated high availability. Those are all great characteristics, and we can debate those all we want to, but really I want to focus on this idea of flexible scalability, because this is really what we're talking about with a lot of these downstream systems when we're interacting with them. All right, so AWS kind of breaks down their services into serverless and some other things. So the serverless services that they have, what I mean by this, and I think what they mean by that is you can just throw a ton of work at it and it will scale up and down. You don't have to worry about it. There's really nothing to manage. You don't have to worry about capacity planning, things like that. Then they've got their managed services. So these are going to be things like Amazon Elasticsearch or Redshift or Fargate or some of these other services that do require a bit of capacity planning. They can scale pretty much infinitely, but you still are going to have to deal with that capacity planning stuff. And then there are things that are not serverless. So really anything running on EC2 would not be serverless. And then there are these other things like Kubernetes. You heard Brett earlier admit that Kubernetes was not serverless, even though Knative may be. So these things I would just say are definitely not serverless. So throughout sort of what we do, we're going to have to deal with all of these things. So an important thing to remember is everything has limits, right? So I said sort of near infinite scalability. The problem is that nothing you deal with is going to be infinitely scalable. At some point, you're going to run out of capacity, and there's more practical limits that are in place, and these are things like reserved concurrency. So you're only going to be able to run so many concurrent functions or Lambda functions. There's function timeouts, right? So I'm not even talking about the 15-minute timeout of a Lambda function or 10 minutes in Azure. I'm talking about you're going to set some of these limits yourself, because if something runs too long, you don't want to just use all that capacity. You're going to want to have reasonable timeouts for your functions. There are memory limits. There is also network throughput, right? We have that speed of light problem. It takes a while for some light to get from Cardiff all the way to US East 1. So you're always going to have issues with network throughput. And now some of these things, some of these services are better than other services. But it's just important to know your limits. And AWS actually does a really good job of publishing what all of the limits are. So as long as you understand those, you're in pretty good shape. All right, so let's look at what I like to call a simple serverless web service. This is essentially a client that communicates with API gateway, hits a Lambda function, maybe connects to something like DynamoDB, and then returns that data back through to the client. So the good news is that API gateway is ridiculously scalable, and Lambda is very, very scalable, and DynamoDB is very, very scalable. Does anybody remember the band Dire Straits? And they had a song, early 80s, that was Money for Nothing. And I'll try to sing it for you. It goes something like this. I want my SQL, right? So people still want to use SQL databases, right? They still want to be able to query, do all these ad hoc queries and things like that. So if we take our simple web service and we put RDS in there instead of something like DynamoDB, the problem is that this isn't that scalable, all right? And so this is the not so serverless web service anymore. And I think you're going to have more workloads that look like this than a pure serverless application. So there's a couple of problems is that FAS, right, so functions as a service, don't really play well with relational databases, and this is for a couple of reasons. The concurrency model is every single connection to Lambda has to create a new connection to the database, right? You can't take advantage of connection pooling directly from Lambda. You have a limited number of database connections available, so even if you have a hugely scaled database with 6,000 connections, you could eventually overwhelm that because you're using a connection for every single user, which is not the traditional model that we see when we use connection pooling. And then the other problem is that if there is a direct connection, you have these recycled containers. The Lambda function might go away, and it doesn't necessarily tear down that connection. All right, so what are some ways that we could manage these DB connections for us? All right, so we could do something like increasing the max connections. All right, so this is kind of risky because you're going to spike your memory, you might spike your CPU. So even though you say, well, I'm just going to bump it up to 6,000, even though the server is sort of rated for that pool, or the database is rated for maybe 3,000 connections. So this is kind of dangerous to do. You could do something like say, well, we'll just limit the concurrent connections, and that way, basically, our consumers will get throttled, but this can make people angry, obviously. You could do things like lowering your connection timeouts, so hopefully those timeouts might drop off, and those connections will become available faster. This is kind of that cross your fingers strategy. The other thing that you could do is you could limit connections per username, so you could make sure that parts of your application get more database connections than other parts. That's kind of a roll your dice type strategy. And then the other thing you could do is you could close the connection every time, open a connection and close a connection on every single invocation. Please don't do this. It's a horrible idea. It adds at least 100 milliseconds of connection time plus overhead to the database to create those and tear those down. So all of these are really, really bad ways to manage our database. All right, so let's look at some better ways to do this. So the first thing we could do is implement a good caching strategy. This is just sort of distributed systems 101. The other thing we could do is we can buffer events, right, especially for high write throughput applications. So we can buffer those for throttling and durability. We could utilize a proxy service. This is something that's becoming a little bit easier to do. And finally, we could potentially manage connections ourselves. And we'll talk about each one of these. So these are better ways in which we can manage. So let's look at the caching strategy. So typically, let's say we have this application, contact Lambda. We want to get to RDS. Now, we're going to introduce something here that's not serverless, right? We're going to put an elastic cache, maybe Redis, in here. But the thing that's nice about Redis is it can accept 60,000 concurrent connections. So even if your Lambda function is going wild, your elastic cache cluster is going to be able to handle that. So, and if you're using RDS, you need to be in a VPC anyway, so you can use Elasticsearch. So essentially what happens is we make a request, we check the cache, simple stuff. If it hits, we respond back, no problem. If for some reason we make this request again and we get a miss this time, that's when we're going to reach into the database, grab the data that we need, write that back to Lambda, and then this isn't a write-through cache, so we do have to manage this ourselves, so we're going to have to write that data back to Elasticache, so the next time we're going to get a hit, and then we write that back to the user. So a couple key points here. You only want to connect to that RDS cluster. My goodness. You only want to, maybe I'll go over here. You only want to connect to that RDS cluster if you actually have a miss, right? So if we hit the Elasticache service and it's a new container and we haven't hit RDS yet, there's no reason to create that connection. So we create that after the fact if we get a miss. The other thing we want to make sure we do is set low TTLs. We don't want our data to be too stale. The purpose of this whole thing is to just reduce pressure on the database because of the connection model, not necessarily because of the scale. And then the other thing that we want to make sure we do is include some way to invalidate that cache. So if you are writing data to the database some other way, make sure you have a way that you can clear out those keys so that data doesn't get overwhelmed. Now, if anybody here has a computer science degree, you're probably saying, my computer science data professor told me you should never put a cache in front of a database in order for you to build up or to provide, to basically amplify or protect against the weakness of that database. That database should be enough to handle everything. I totally agree, right? So you still need to make sure you size this database correctly. We're putting the cache here, maybe not because we're getting better performance, but simply because we're trying to mitigate that. Connection issue because there's no connection pooling. So just something to think about there. All right, so the other question is if we're doing a heavy write application, we're sending a lot of data into our database, the question is, do we really need to know that the data actually got into that database and was written correctly? So we're very familiar with this idea of synchronous communication. This is pretty much the standard that we've known since the beginning of the web, that we make a request, that request does something, gets data back, and sends it back to us. We wait for that entire process to happen. This is a blocking request, right? We have to wait for everything to work, and also if something is down, then we have to fail the whole entire job. But with distributed systems, there's a much better way. It's called asynchronous communication. These are non-blocking requests. This allows us to essentially hand off the event and say, hey, tell me that you've got this event and you're going to do something with it. We can use a much lighter weight transport to do that, and we don't have to worry about writing it to a database that could potentially fail or something else. So what's great about using this asynchronous process is now we can do a couple different things. Not only can we buffer events to make sure we don't overwhelm those downstream systems, but we can also add a level of durability to that. So if we take our application again, and this time we want to go to RDS, instead of writing directly to RDS, we're going to put an SQSQ in front of there, okay? And an SQSQ is very, very lightweight, highly distributed. The chances of this thing going down is very, very low. But what happens is our Lambda function is actually going to make sort of an asynchronous request. We're going to say, hey, SQS, take our event. And SQS says, OK, I got it. And then we can respond back to the client. And we're done at that point. The client now says, my event was accepted. Great for things like webhooks or anything, any type of event streaming, something like that where you're accepting a lot of events. So then what we do is we put a Lambda function in here that is throttled. So we set whatever the throttling is. We want to sort of limit this so that it matches whatever our throughput is to our database. This happens all the time. That database may have 1,000 concurrent connections available to it, but then all of a sudden we get a huge spike, and we get all of these events coming in. We would overwhelm that database and shut it down. This way, we add the durability. We make sure it goes into that SQSQ. Our Lambda function can then pull that SQSQ. Right? This is a synchronous request, writes it to the RDS cluster, that sends it back and removes it from the queue. The cool thing about this is, let's say that the RDS cluster is down. There's some failure somewhere. If that fails, then we can actually take that data and automatically write it to an SQSQ with a redrive policy. So this allows us a bunch of different cool things, like being able to see what the events were that failed, being able to replay them. So a couple key points here is, SQS is going to add a ton of durability to this process here, right? And you're going to allow you to throttle those events so you can match that throughput and really reduce pressure on the downstream. And then also those failed events are stored, and you can just easily inspect those and replay those. Now, another thing that I think is becoming very popular, people are starting to wrap their head around this, is you might say, well, why do I need 2 Lambda functions? It seems kind of crazy. Well, you actually don't necessarily need 2 Lambda functions in this situation, depending on what type of data you're doing. If you're not really transforming the data, or even you're doing minimal transformations, you can use service integrations with API Gateway, and you can actually just write the data directly into SQS, and then your Lambda function that processes it can do some of the validation and some additional work, and that just makes it Super easy. You save yourself all that money on the Lambda function, and then your code, you don't have to worry about your code having some sort of problem. So this is a very, very interesting way to do it. It's something to look at. I do this for like a Twilio webhook and a couple of other things where we write the data right into SQS. All right, so utilizing a proxy service, right? So you may have heard of something like PG Bouncer. You may have heard of something SQL Relay. Typically, you have to install these on some sort of compute environment like EC2. If you put this in the context of a serverless application, then this is kind of one of those things where you're like, this looks kind of ugly here, right? Makes the kitten cry. So at least you could do something like this is maybe run that on Fargate. We also have the new Amazon RDS Proxy, which does some proxying for us. This is still in preview, and again, it's only for AWS, so if you're working with other services, it might not be the best. Obviously, wouldn't work for you. All right, so the other option is we could manage connections ourselves. If we did this, we would have to count open connections, we'd have to close connections if the connection ratio was too high. We would have to close sleeping connections if they had high timeout values, and we would have to retry connections with some sort of exponential backoff. And you're probably thinking to yourself, this sounds crazy. You'd have to be a crazy person to write something like this. I am that crazy person because I needed it. So what I did is I wrote this, node module called Serverless MySQL. I'm not telling you to use this. I'm not trying to sell this to you in any way. This only works for MySQL, and it only works for Node. But what I did want to do is show you the process to understand what you could do if you did want to implement something like this yourself. So the first thing we do is we have to count open connections. We can use the process list to do that. That's pretty straightforward. We can look at the connection ratio based off of what we just pulled back. If it's over 70% or something like that, we can remove that. We can check what the highest timeout is, so we know if there's connections we can clean up that are past our zombie times. We can try to kill those zombies. If there's no zombies, we just terminate the connection. This is that just to make sure that we open up more connections and kill some zombies. The other thing we can do is we can look up how many open zombies there are based on that timeout, and then we can kill those zombies. And then finally, we can implement something like a retry policy or retry those connections with something like jitter, which is an algorithm that allows you to do sort of a scattered retry. So you're not doing like just an exponential or just something that's very predictable, which could overwhelm the system if everyone's trying at the same path. So question is, does this really work? Well, I took an Aurora serverless cluster with 2 ACUs with 90 connections available, a gig of memory in the Lambda function. I tried 500 users per second for a minute. The average response time was 41 milliseconds, and there were 0 errors. Please hold your applause. The key about all of the stuff we just talked about, though, is that we shouldn't have to do these things, right? So we've got Aurora Serverless, which was something that was released by Amazon, which is a pretty good service, right? But it doesn't take care of that max connection issue for us, right? We're still going to have that max connection issue. We have the Aurora Serverless Data API, which I absolutely love this service. It's really great. It runs outside the VPC. It's HTTP. They just added VPC endpoints for it, too, so that you can, if you have something in your VPC and you want to use this, you can do that. The problem, though, is that it is kind of slow. For the most part, it's fast, but really for synchronous invocations or synchronous processes, this is not the best solution, but it does work great for asynchronous stuff. And then obviously we have the Amazon RDS Proxy. Couple things with this is an added service that you pay for on top of your database. And it doesn't solve the RDS problem or the relational database problem of scalability anyway. So if you do have a really big workload running on RDS, this will help solve the connection issue problem, but it's not going to solve the larger problem of scalability. And again, this is also in preview mode, so it's not quite ready. Hopefully it'll be ready soon, and it's something that you can utilize if you have those workloads. All right, so third-party APIs. This is another thing that we have to deal with quite a bit. These will always most likely not be serverless, or if they are, we won't know about them. So a couple things that we can do to make sure that we are smart about managing those calls. We can implement a good caching strategy, just like we did for RDS connections, and we can do the same thing and make sure we buffer our events so that we get that throttling and durability. If we're writing to an API, we want to make sure we don't overwhelm that API. We can throttle those and make sure that we don't lose any events in the process. And then another thing we can do is implement what's called a circuit breaker. If you're not familiar with circuit breakers, it's sort of a distributed system pattern. And it's very, very interesting what it can do, because this allows us to make sure we don't send too many events to an API that might be down. So if we look at this pattern again, we've got our same thing. We got API gateway hitting a Lambda function. Now let's say that we want to call the Stripe API. The happy path is we send a request to Stripe, Stripe processes it, send it back to us, and that goes all the way back down to the client. But as we know, as Werner Vogel says, the CTO of Amazon, everything fails all the time, right? So even if the Stripe API is the most reliable thing in the world, the connection to it might fail. The connection coming back might fail. There might be some other error. An event might get lost. So we want to make sure that if an API goes down and something maybe not as robust as the Stripe API, we want to find ways to deal with it. So what we're going to do is we're going to introduce a status check. Every time we go to call that API, we're going to check this status call or check this status mode, and we're going to either use something like DynamoDB or even Elasticache in order to store the state of our API. So what we do is if the status check says, hey, the API is green, we send a request to it. We call that a closed connection, because electricity, if you think about it, when it's closed, that means that the data can flow. That responds back. Everything is great. If there's a failure, then what we want to do is slowly increment some sort of failure count in the cache for us that tells us, OK, we've now exceeded 1,000 errors or something like that. And we can respond right back to the customer and say, OK, the API is not working. And this client, by the way, does not have to be a web browser. It could be the other side of an SQS queue. It could be Event Bridge. It could be something else that's sending that data back. So what we want to do is, now if the next call comes in, we're going to fail, and we can immediately respond back to the client, right? And we're in this open state. The reason why this is extremely important is because if that API is having problems, like let's say there's slow processing or there's some error or part of the network's out or whatever, if we keep sending events to it, we're going to be part of the problem. We're going to DDoS, the application that we're using, and we're going to make it worse. So the best thing to do is identify that there's a problem, stop sending data to it. And if this is buffered some other way, like with SQS or whatever, then the impact is going to be very, very minimal on our side, but it will allow that API to recover. So the thing is, though, is that we can't just stop sending requests and then never check it again. So periodically, we send what's called a half open, or we half open our circuit, and we send a request to it to say, hey, are you working now? If it fails, fine. We just say, no, it didn't work, that's fine. But if it succeeds, then what we want to do is make sure we update our cache, say, hey, great, we're ready to go. And now from this point forward, we can go ahead and flip it to closed circuit, and all of our data will start flowing again. And again, if you have this buffered and you have that data in SQS or Kinesis or something else, all of those events will flow through again. So a couple of key points here. You want to make sure that you cache your cache within warm functions. We do not want to be calling Elasticache or DynamoDB on every single invocation, right? Maybe we check it every 100 calls, depending on your velocity and things like that. The other thing you want to make sure we do is use a reasonable failure count. If you have 1,000 requests per second, we don't want to fail after 10 requests are bad, right? We might want to fail after 5,000 requests are bad. We want to make sure that the API itself is actually down before we start failing all these requests. If you have 10 requests per hour, then you might want to fail after one, for example. So the other thing you have to do is understand item potency. Item potency basically is the idea that an event has to be unique. And so with something like the Stripe API, you can send in an ID that is called the item potency ID that will identify that it's a duplicate event, but other APIs might not do that. So if you do have a requirement where you can only send the event once to that API, that's just something you have to think about and deal with. All right, so what about quotas? So quotas are a little bit different than just throttling, right? So concurrency has no effect on frequency, which means if you have an API that only accepts 250 events per minute, you can't just set your Lambda functions to 250 concurrent events, because if it only takes half a second to process that, then you'll be sending a lot more requests than the API can handle. Stateless functions are not coordinated, right? So there's no way for one function to know that it's over quota other than checking something else. Step functions, the standard step functions would be extremely expensive for something like this, especially for a high velocity workflow. And then adding state to each individual Lambda function basically would still require the Lambda function to run, check something and say, oh wait, I'm over quota, so now you're running all these Lambda functions and it makes no sense. So there is a better system that we can build. It would have to be 100% serverless, cost effective, scalable, resilient, efficient, and coordinated. So there's something called the Lambda Orchestrator. I'm going to go through this very quickly because I'm running out of time. There's a QR code to find the blog post that talks about this. But essentially, if we have our Gmail API and it's got a 250 quota limit per minute, then we would create a Lambda function with a concurrency of 1, queue all our events, use DynamoDB or Elasticache as a cache to control, to understand whether or not we're over quota, schedule a rule every minute, and essentially what this would do is it would implement something like this, the circuit breaker pattern, right? So we can send bad events to a SQS DLQ, implement that status check, fan this out so that you can have multiple workers running. But again, this main Lambda orchestrator is understanding where the current quota limit is. So these process individual events. They call the Gmail API. Again, you can handle failures. Again, I don't have a lot of time, so take a look at that if you want to see it. But essentially, this allows you to manage those quotas. I know it looks a little complex. It's not quite as complex with this. It's really only 2 Lambda functions. But this way you can do the failure modes and some of that other stuff and pass them through that way, do your half-open stuff, update if it passes, and then you're back off to the races there. All right, so let's talk about decoupling our services. So SNS, for example, is a very good service where we can take a request. It handles that asynchronous process for us. This is asynchronous so that you can just say, hey, you get this event, and then I can disconnect my client. This acts as its own little event service. So you can fan this out to SQS and email and HTTP calls. You can send APN messages, all kinds of cool things you can do. You can even trigger a Lambda function. If it fails now, they've just added DLQs, so if for some reason this doesn't get distributed, you can write that to a DLQ. So a couple key points here. SNS has a very well-defined API, so if you wanted to use this as a central communication bus, you could do that. And now with the DLQ, it's kind of very useful if you wanted to use it for that purpose. This does decouple all of our downstream processes, so we don't have to worry if we have to run 5 or 6 downstream processes on the other end of an event. And you can be very selective about what gets triggered based off of these filters. The other thing here, there's a fun fact, SNS to SQS is pretty much guaranteed. There's 100,010 retries. So I like to say, like, when the zombie apocalypse comes and everyone's wiped out, SNS will still be delivering messages to SQS. All right, so then Event Bridge is sort of a new way to do this. Sheen talked about this, so we won't spend a ton of time on this. But essentially, this is very similar to what SNS does, only it's got a lot more features, right? So we can distribute this to SQS. We can send it to Lambda. We can send it to things like step functions. We can even send it to other accounts, plus there's 16 other integrations that this thing does. So some key points on this is this allows for multiple subscribers using rules and patterns and filters, which some of that stuff is new, so you can do some really cool stuff with that. You can forward events to other accounts, and it's got 24 hours of retry built in, which is pretty cool. So just quickly to go through this idea of what you can use it for is all those patterns we just talked about. You send your message to Event Bridge responds back to your client, whatever that is, says we've got it. Now you can add all of these different services, right? So we add a rule that is attached to that service. Anything that comes through Event Bridge that we want routed to that service, we can take advantage of all those cool things that we just learned for throttling and for circuit breakers. We can do all that through there. So now you've got, let's say, an SMS alerting service. You've got a rule for that. You could have a billing service. You've got a rule for that. And you can create these filters that say only execute this if it is order complete, or only execute this if the value is above a certain amount of money. So very cool stuff. So you can filter those events selectively. You can manage the throttling per service. So each one might have different characteristics for throttling. And then you can use Lambda destinations with asynchronous. So if you call Event Bridge asynchronously, or sorry, if you call your Lambda function asynchronously, you don't even have to write code to integrate with Event Bridge. It can just automatically happen as part of a Lambda destination. All right, so quickly, almost done. Other non-serverless components, we've got managed services out there. We've got other cloud services like Atlas or maybe Elasticsearch or something else that you're interacting with. You've got legacy systems you might have to interact with. And we might even have our own serverless APIs, okay? So our own serverless APIs that are serverless might have other non-serverless components downstream. So we have to think about all of these ways to manage those different downstream services. So finally, non-serverless components are inevitable. You have to know the limits of your components. You have to use good caching strategies. You have to embrace asynchronous processes to make sure you decouple those things. Buffer and throttle those events so that we don't overwhelm downstream systems and we don't lose events if something fails downstream. And then we didn't really talk about this, but eventual consistency is this idea that eventually the data gets to where it needs to. And if there's a little bit of delay, this is part of distributed systems. Works really, really well. Something to understand, look it up if you're not sure what that is. These are a couple of things that I'm working on. The podcast, I've got a couple of open source projects and so forth. I'm way over time. Thank you very much.